Hey guys, today we are going to analyze potential energy diagrams, and they can be a little bit tricky. So I am going to do the first example with you and then have you guys do the second problem independently. So I'm going to go ahead and make a copy of this assignment and walk you through the first diagram step by step. So definitely be sure to watch this before attempting on your own. Also, if you haven't done your notes for this lesson, you want to make sure those are done, because if they're not, a lot of what I'm saying is going to be like Greek to you and you're not going to understand the terminology. So just make sure your notes are done and in front of you before attempting this assignment. Okay, so what we're looking at here are potential energy diagrams. Again, I'm going to do the first half, so diagram A, and then you guys are going to do diagram B, and then also that last question 13 on your own, okay? So this is just a practice worksheet. You're going to type your answers directly in, and then also if you could highlight your answers or just change the color of the text of your answers, it'll make it easier for me to grade. All right, so this energy diagram is showing us the energy of a reaction. So what's happening to the energy as a chemical reaction is taking place. So question 1 asks us, and again, we're looking at diagram A. Question 1 asks us, is this an exothermic or an endothermic reaction? So looking at this right off the bat, I know that this is going to be an exothermic reaction. Okay, so the answer to number 1 is exothermic. And the reason I know that, which is going to be the answer to question 2, it says, how do you know what kind of reaction this is just by looking at it? Because we haven't done any calculations yet. So when I look at this diagram, we have to remember from our notes that if the energy of the products are lower than the energy of the reactants, then it is exothermic. If it's higher, it's endothermic. So when we're looking at this diagram, the line right here represents the energy of the reactants. Okay, so the reactants that are on the left-hand side of the equation, these are the energy of the reactants. The energy of the products is on the right-hand side. Okay, so if my energy of my products, this line right here, is lower than the energy of my reactants, which is right here, I know it's exothermic. Okay, now if this line was higher, so if my energy of my products were higher than my energy of my reactants, then it would be endothermic, okay? But in this case, it is exothermic. Okay, and how do I know by looking at it? What I just explained, the energy of the products are lower than the energy of the reactants, okay? All right, now number 3 asks us to determine the heat of the reaction, delta H, for this reaction, and show your work below. So delta H is the change in enthalpy. Okay, so we're looking at the change in the energy of the reaction. So when we're determining the heat of the reaction, we are going to take the energy, the ending energy, so the energy of the products, and we are going to subtract the energy of the reactants. Okay, so if I'm looking at this diagram, my energy of my products is 60 kilojoules. Okay, because if we look on our y-axis is in kilojoules, so we're going to do 60 kilojoules minus the energy of our reactants, which is 120. Minus 120 kilojoules. So that means, also these J's need to be capitalized. It's going to bug me if I don't fix it. So that means that our overall energy of our reactants is going to be negative 60 kilojoules, which makes sense, right? Because remember from your notes, an exothermic reaction will have an overall energy of a delta H that is negative, right? So if the delta H of a reactant or a chemical reaction is negative, that means it's an exothermic reaction. So that does make sense, and that lines up with what we said in number 1. All right, question 4, determine the activation energy for this reaction, and we're going to show our work. Now, remember, our activated complex is the peak here, right? So this is where we're getting that transition where our products are starting to form. So to determine the activation energy, which is what we need in order to actually start our chemical reaction, we are going to take the energy of the activated complex and subtract the energy of the reactants. Okay, so whatever is the peak minus our first line here, that's going to give us our activation energy. And remember, catalyst, the function of a catalyst when you add it to a chemical reaction is to lower the activation energy. Okay, so we have to keep that in mind. That is a review of biology, but just throwing that out there. Okay. So if I'm taking a look, my activated complex is 220 kilojoules. And then again, our energy of our reactants is 120. So we're going to do 220 kilojoules. 220 kilojoules minus 120 kilojoules. And that is going to give us an overall energy of 100 kilojoules. So that means the activation energy for this particular reaction is 100 kilojoules. Okay. So again, the energy of the activated complex, this is not a calculation, you just have to identify it. And we already did that in number 4 to help us determine the activation energy. So again, we're just going to look at the peak of this little bump, right? So this is where our activated complex is. At the peak, that's going to tell us the energy of our activated complex. So that is just 220 kilojoules, right? We're just following it over to the y-axis to see what it corresponds with. So that's going to be 220 kilojoules. Okay. And last but not least, question 6 is asking us, what would the reverse activation energy be for this reaction? So remember, when we talked about chemical equilibrium, we found out that most chemical reactions are reversible, right? They can happen in the forward and the reverse direction. With these potential energy diagrams, we read them from left to right in the forward direction, right? But if we looked at them backwards, so from the right to the left, that would be the reverse energy of the reverse reaction. So instead of calculating the difference between the activated complex and our energy of our reactants, we're going to calculate the difference between our energy of our activated complex and the energy of our products, right? So we already know that the energy of our activated complex is 220. So it would be 220 kilojoules minus the energy of our products, which is 60. And that is going to give us an overall energy of 160 kilojoules. So 160 kilojoules. Okay. And now this would be an absorption. So I'm just going to go ahead and write absorbed. Okay. Now again, because this is in the reverse direction, remember, so in an exothermic reaction, if this happens in the direction of left to right, energy is being released. Okay, so that energy is released. However, if we're looking in the reverse direction, that energy is being absorbed. Okay, so it would be vice versa with an endothermic reaction. So just keep that in mind as you are doing these diagrams. Okay, so that is how you answer those questions. I tried to do it quickly so that you didn't have, another super long video to watch. But those are the answers to diagram A. You guys are going to do diagram B on your own. Okay, so it's the exact same thing, same process. It's just a different type of diagram. For number 13, it's asking which diagram represents each of the following scenarios. So it gives you a scenario of a particular chemical reaction or change of state of matter taking place. And then it asks you basically to identify, would this be exothermic or endothermic? Okay, so we already know that diagram A is exothermic. So just read through these and try to determine, okay, is energy being released or is energy being absorbed? Okay, I can tell you right now for burning logs, like when you think about a chemical reaction of anything being combusted, energy is going to be released, right? You can stand by a fire, you put your hand by the fire, you can feel that energy being radiated off of it. That is going to be exothermic. We know that diagram A is exothermic, so we would put A for that one, okay? So try to read through those, think critically about those, and answer them. Some of them might be a little bit tricky. If you have questions, you can always ask me, but do your best to think through those on your own and try to figure those out.